Kalispera σας. Good afternoon. It's my great pleasure and honor to host my good friend Anthony Chronopoulos, Dr. Anthony Chronopoulos, whom I met a long time ago in Minnesota at the University of Minnesota at Minneapolis. And then he is now affiliated with the San Antonio University of Texas, and also at the Advanced Science.
Nothing else. The co-author is.
Huh?
My co-author is.
Okay, and this is the co-author of this work. And Anthony is working in linear problems mostly, and today he will talking about iterative methods on Krylov, nested Krylov methods for the solution of linear systems and applications. And the floor is all yours.
Thank you so much. It's a great pleasure to be at your university and your beautiful island, and give this lecture on our work on Krylov iterative methods for linear systems and applications. So the introduction, we consider an end-by-end linear system, HU it would be, with a non-symmetric matrix, sparse in general, and B is the right-hand side. It's the right-hand side, okay, and U is the unknowns vector. A Krylov subspace method is a iterative method based on vector projection expanding Krylov subspace, which is this is a starting initial residual vector. The matrix times that vector and powers of it. Okay. Now, so I'm giving some introduction notes before I even give the structure of the talk. So a left preconditioned linear system is equivalent to solving the linear system multiplied by an approximate inverse of the matrix H, multiply from the left-hand side both H times U and the right-hand side. Examples of preconditioners are incomplete LU decomposition or a fixed number of a static iterative method, which we'll call SIMT, for example, Jacobi, or a fixed degree matrix polynomial, or a few iterations of another KSM, Krylov subspace method. Nested or flexible or in or out iteration KSM are KSM where we have a preconditioned KSM that has an outer or main iteration and an inner iteration applied to obtain an approximate solution at the preconditioning step of the outer iteration. Related works on this are from various well-known people such as Axelson, Vasilevsky, Saad, van der Waals. In the past works, it was observed that empirically the nested KSM outperform, that is, they're faster and more efficient than standard KSM. For example, restarted methods such as GMRS or truncated methods such as Orthomin. The generalized conjugate residual is a method, restarted method, on which Orthomin is based, is the mostly used KSM as an outer iteration because it allows direct control over reducing the residual norms. And the third remark is none of these works has considered constructing and studying nested truncated KSM. So here is the outline or structure of this lecture. Review of the residual cutting method is the new method which has been proposed in past work. A proof that RC is equivalent to nested Orthomin. Orthomin is a well-known and widely used Krylov subspace method with a variable preconditioning. The generalized RC and a proof that it is a KSM, a stable GRC algorithm based on modified Gram-Schmidt, a proof of the convergence of GRC, the minimal residual as an inner loop method in GRC, the preconditioned GRC, then applications from sparse matrices, numerical experiments, results and discussion, conclusions, and future work. So we'll take one by one. But I apologize. I have followed the flow of the paper, but I will go forward and backwards a little bit. Otherwise, it's difficult to understand. So here we say we see RC algorithm, and I will go to that first, and then I may come back to this slide. So this is the RC algorithm for iteratively solving the linear system of equations that I showed in the beginning using a nested Krylov subspace method, which is the RC algorithm. So the initial vectors that are the inputs, initial vectors for the solution, and the residual vector is computed from the right-hand side, h times the initial solution vector. Then we have the outer loop, okay? And in this step, we compute an approximate solution where the right-hand side is the residual vector. This is the inner loop. This is a preconditioning step, okay? This is what it makes it a nested method. Then we solve a least squares problem. I apologize, but it needs too much pressure. So I will point here. So we have to solve the linear least squares problem in Euclidean norm to find an approximate solution to this problem. We find the approximate solution, then we solve the linear least squares problem to find these parameters, scalar parameters, to optimize in that sense, minimize the norm, clear norm. Okay, and then this is no good either because it shows face. So then we improve the solution, the approximate solution, by adding this optimized approximation and compute the residual, the new residual. At the end, when we're satisfied with the convergence check, we output the approximate solution and the residual. Okay. So I will go back now, and I understand I'm not in the mathematics department, so I have to not to spend too much time with theory. But here are the assumptions. So these vectors are the solution vector, the residual vector. This is the direction vector. This is the solution to the inner loop approximation. And this is the direction vector as well. We store several of these up to m, okay? Actually, up to j. M is the outer iteration, and we store j of these. This UF is the approximate solution of the least squares problem, okay? The residual error vector and the approximate solution of the residual error equation, okay, which is the preconditioning step, and this is the direction vector. And so the least square solution is these scalars that minimize the Euclidean norm of the residual. We'll use NRE. And RC is a truncated method and saves the J most recent direction vectors. Okay. We'll see that again here. So these are the direction vectors. They're used here. Okay. This is the solution of the approximation or the preconditioning step. And we certainly, once more, have to compute these scalar parameters in minimizing the Euclidean norm of the error here. Now, as a preconditioning step, we can use, as I mentioned, the incomplete of decomposition, or we can use something similar as the Jacobi. I will write something here on the board, and I apologize. I should have made a slide on this. Okay. So the Jacobi method. For x equals b, this is the diagonal of h. Okay, it's like this. It's identity matrix. Okay, for simplicity, we assume that D is identity. Okay, so we have somehow done the scaling by the diagonal, the inverse of the diagonal. So we just take then this as the Jacobi iteration. Okay. And if we do this, then we need to start somewhere. So we need nx0, and I will come back there. I will write this equation, and I will come back there. In the inner loop of the nested method, we can take as x0, so we have two cases. For example, this is one of them. Then this is the approximation, or for example, take x0 to be 0, and get this one. Okay. So let me so here for this, as I said, we need an approximate solution. One simple way to do that is the static iterative methods such as Jacobi. Okay. Now I show you the Jacobi, and then I bring it to this linear system, okay? And you have this first one, Cm equals identity minus h, Pm minus 1 plus Rm, or you can have the second one. And so this is one of them, or this one, okay? Second one, C. This is the simplest one. That is essentially no preconditioning, okay? This is the identity vector, okay? Now this equation is a variable preconditioner. Why is that? Because this phi is from the previous step of the outer loop. Previous outer loop. That is, while we're solving this, we're using at step m, at iteration m, we're using some information. Okay, some information from m minus 1 step. Okay. So this is a variable precondition for that sense. That is, doesn't use information from the m step. Okay. But if we're doing this kind of preconditioner, then this is not a variable step. Okay. All right. So now the other important step that must be done is step 4. Somewhere is my pointer. I don't know where it is. Yes. So this step is very important. Very, very important. And you can solve this first problem either by classical Gram-Schmidt, where you have to orthogonalize these vectors, or by modified Gram-Schmidt, which is a stable process. So I will skip this for a moment. Okay. We'll go to where is it? No. Let's go back. So okay. So let's first say the results based on what the classical Gram-Schmidt. So this method is the residual cutting method, and the authors of my collaborator thought that they had a completely new method. It is a new method, but it's not a completely new method. So essentially, this RC method solves using classical Gram-Schmidt the least squares problem, and it's equivalent to Orthomin. It's an old method, well known and widely used, with variable preconditioning. It's exactly this. Okay. This is used in the preconditioning step or the inner loop, and then they use classical and Gram-Schmidt here. Okay. And this really is Orthomin with a variable precondition. I mentioned why it's variable. Okay. There's a proof here, but I will skip it. Okay. But they use classical Gram-Schmidt. Now, my co-author, when we started, had tried to extend this to the so-called generalized Gram-Schmidt. And he took as an approximate solution to the preconditioning step, to the inner loop that is, he defined a function g based on the previous outer loop direction step, the matrix and the residual vector m, where the g function is either linear or constant matrix polynomial. And then I told him that we can extend it to any matrix polynomial greater or equal to 2. Okay, so we considered really, truly generalized in that sense. Okay, so here are some examples. When it's constant, it's essentially no preconditioning at all. If you apply a fixed number of consecutive iterations of a sim, okay, for one step of the Jacobi iteration, this is the variable conditioner. You can do with 2, okay, you can do 2, etc. You can do with 3, etc., etc. Okay. In order to do all of these, you have to take this one and write it out. For example, and use it for the inner loop. For example, to get the last one, the last line, you have to write from here. You have to write 2 steps. So you will do like this. It's very important. It's a basic thing, but it's very important to understand how this is obtained, because we'll use it later on as well. Okay, so this would be this case when x0 is pm minus 1. Okay. Now the GRC algorithm is essentially an extension of the RC algorithm, and the only thing that changes is this step here, which is the inner loop or preconditioning step. Okay, the remaining parts, the remaining steps of the algorithm are the same as the previous algorithm, which is RC algorithm. Okay, so as I said, there are other choices for this function. For example, this choice, or many other choices for the psi, for the g function exist, but you have to come up with it. Okay, but here for simplicity, we just base our polynomials, matrix polynomials, on the Jacobi. Okay. We are able easily to prove that the GRC method constructs a Krylov subspace at each iteration. It's very important to have a Krylov subspace. I will not go into the proof of this, but it's very important because all the theory that has been developed about the Krylov subspaces also works here. So it's very important. Okay. For example, if instead of this Jacobi here, we used other static methods like Gauss-Seidel, that would not be the case. There would not be Krylov subspace. Okay. So the corollary is that assuming that GRC least squares problem is solved with the classical Gram-Schmidt, then GRC is equivalent to Orthomin J with a variable preconditioning. So a well-known method. The authors and the authors of my co-author did not know this before. Something new here, because they were physicists and they did not know very well numerical in algebra. So we have to point this out. Now we come to the modified Gram-Schmidt algorithm. It's well known that the Gram-Schmidt, the classical Gram-Schmidt, is unstable. Okay, it's well known by all mathematicians method to create orthonormal subspaces, basis of subspaces. But in numerical linear algebra, it's known that it's an unstable process. So we use the modified Gram-Schmidt, and we see here the modified Gram-Schmidt, assuming some vectors, J vectors, Pi, and we have this double loop. The essential thing is that each vector is being modified itself every time before it's used. Whereas the classical Gram-Schmidt, if you remember, you assume the basis we had before, and you just use it. But here you modify the vectors each time before you use them. The important thing is, and at the end, here we get the norm, the Euclidean norm, and we divide by it the coefficients. So essentially, at the end we get an orthonormal, a set of orthonormal vectors. Okay. So the important thing to know here is that this method, the RC method, which is equivalent, as I said, to the Orthomin, builds an initial set of vectors, those direction vectors phi, and then it omits one, adds one. Okay, initially it builds up to J vectors. J could be 5, for example. Okay, it builds from 1, 2, 3, 4, 5, and then it's a window of 5 vectors that moves along, drops the first one, the oldest one, and adds the newest one. And so it is very important to use this. It's not that we have these J vectors, fixed number of J vectors. There's one which is being added every time, and one which is dropped from that set of vectors. So we assume that we have an orthonormal set, and we need to add another vector to complete it to J vectors, which are normal. As I said, J, assume that J is 5, for example. So we have to apply a subcase of this algorithm called algorithm 3.1 to compute, by computing the entire inner loop only for k equals J. So only for this last index only, okay, of the outer loop. And so we denote the output of this algorithm in terms of linear combinations of a set of vectors in brackets, in curly brackets, using the same scalars produced by the algorithm. So the Pj, that is, which will be added, is the linear combination of these already orthogonal vectors, if you like. So the generalized residual carrying method requires the solution of a least squares problem of solution of dimension n by j in each iteration. We apply the modified Gram-Schmidt to create recursively orthonormal vectors from these vectors, h times phi m, at each outer iteration using the modified Gram-Schmidt. Then we can solve easily the least squares problem. In this method, which will be called GRC MGS, the CM is the solution of the inner loop iteration at the outer loop iteration M, and phi m is the linear combinations of the vectors CM and these phi with different indices here. And we come to this algorithm now. I have to exercise my fingers due to the difficulty with the pointer. So this is GRC-MGS, which is a stable version of the algorithm. We have the initial vectors for the solution and the residual, initial residual, and then the outer loop. And the first step of the outer loop is the inner loop here, where we'll compute with one of these, let's see, M, one of the several choices actually, okay, matrix polynomial here. And we apply the algorithm I just showed you for the modified Gram-Schmidt to get the orthonormal set of vectors. We have already these, as we assume already that these have been normalized, and we add a new one here, okay, which is from this solution times the matrix on this vector, and we compute this as a linear combination of these vectors, and also at the same time we compute the linear combination of the direction vector using the same scalars in this linear combination. Okay, so we have these two new vectors, and then easily can be proved mathematically that the solution of the least squares problem that was involved in the RC method and also in the GRC method essentially needs just a new scalar which is computed this way, because of the modified Gram-Schmidt and the classical Gram-Schmidt. That least squares problem is solved with a diagonal, basically inverting a diagonal. Okay, so from iteration m, we can move to iteration m plus 1 by just computing the residual this way and the approximate solution this way. And at the end, when convergence is satisfied, convergence test is satisfied, we output the solution and the residual. I will not deal with too much of this theory, but I will say the theorem and maybe one or two relations. So this is pretty standard in proving the convergence of this Krylov subspace method. Assuming that H is non-singular and the residual Rm is non-zero for some m, then we also assume that we have a Krylov subspace approximation in the, a polynomial approximation in the preconditioning step. That is, it's a fixed degree polynomial, as I mentioned already, with a positive definite symmetric power. This is important. Then the following relations are true for the direction, the residual vectors, okay, generated in the GRC method. For example, we have these orthonormal because we created them, and so on. I will only focus on this, that the solution, the approximate solution, step m, minimizes the Euclidean norm error over the space of these vectors. It's a subspace. Okay, it's an affine subspace. Okay, and And so this is easy to prove and we'll not deal with it. It's in the paper. And under the assumptions of this theorem, TRC produces a non-zero scalar in the improvement of the solution in the algorithm that we go back. So that is, this would be non-zero, if I find it. AM would be non-zero. Sorry. This AM would be non-zero, and there is substantial progress towards the solution. That's important, okay? And another theorem, which is also very important, is what happens with the errors in the inner, the relation between the errors in the inner and the outer iteration. So in this algorithm, we said already many times, we will solve this approximately only, okay? And so there is an error here, and so we're not interested to drive it down to machine precision, okay, to go to the error tolerance of the outer loop. And then there is an error in the residual error. Okay. These are related, and it's very important to have an inequality that relates them. So the norm of the residual error in the outer loop and the inner loop are related like this. Okay, this is the outer loop, and this is the inner loop. Okay, and so if you have a good but not still coarse approximation, not very fine approximation in the inner loop, that is, you do some approximation but not to the tolerance that you want the outer loop. That means that you have a constant delta less than 1 and positive, so that you have this inequality. Then you have monotone convergence, okay, of the outer loop. That's our goal. Our goal is to have good convergence of the outer loop, monotone convergence if possible, and this is important, and we get that. This Jacobi with modified Gram-Schmidt is good, but there's something even better. You can use a minimization method inside, error minimization, inside as an inner loop. Okay? And we thought about using the steepest descent method, okay? Or minimal residual method. It's also GMRS1, whatever you. This is from Cauchy's years. Okay, it's in mathematics everywhere. So at each iteration of the minimal residual, the parameter gamma is computed to minimize this norm. Okay, so basically you improve the solution by simply minimizing the norm, and that's the parameter you have to use. Okay, that's the parameter you have to use. It's a steepest descent method, and so we'll use this as an inner solver. And if you do that the same way as I obtained here. I expanded here the Jacobi iteration, and then I used this in my inner loop equation. Okay, the same way you can do this. You expand. Okay. You expand two steps. You do two steps of this minimal residual, and then you use this in the equation of the preconditioning step. It comes out to this. Okay. So we must set C M equal to this. This is an approximation in the inner loop of the GRC MGS method. Okay. However, in order to avoid two matrix vector multiplications, because we already have one in the h times the direction vectors, we have one, and here is the second one. In order to avoid that, we simply use gamma 0. There is a gamma 1, it needs an extra matrix vector multiplication, so we use simply gamma 0 here. So this is an engineering trick. No engineers do that. You do this and see what happens. Okay. So there are various choices for this inner loop approximation C, but we consider here a few simple ones, and then we also consider them in the context of the preconditioned linear system. This is the preconditioned system. So this is the C of the variable preconditioning in the Jacobi, the first one. So we have, okay. The second one is nothing, no preconditioning at all in terms of the Jacobi. This is the standard RU preconditioning. So this is left preconditioning. We'll use RU. And here, this is the second choice. Second choice that I have here. And then the last case is the MR, the minimal residual, okay? It's the minimal residual, where you do another minimization in the inner loop, okay? So here is the preconditioned GRC-MGS algorithm, okay? It's similar to the previous one. So I will not go into detail. I will only mention that everywhere we use the left preconditioning. So everywhere you will see the PR combined with the matrix. Okay. Now I will go to the experiment. Before I do, I will mention applications from various sparse matrix models. Okay? For example, computational engineering, aerospace, chemicals, nuclear, petroleum, structural, power system networks, signal processing. Everywhere you have sparse matrices. And the references are there, especially if you go to the first one. They are categorized according to the different engineering, where the matrices, contributed matrices, because there are a lot of matrices, but these are only contributed to that web space, table page. Then we have also computational science, astrophysics, biochemistry, plasma physics, quantum physics, oceanography, and even computer science, okay? Data mining, machine learning. Certainly, these are real. The first one is real problems, which have been examples have been contributed. The second one is a website of somebody who considers sparse matrices for machine learning. It's a very good website if you're interested in machine learning and sparse programs for machine learning. And the last one is the gallery from MathWorks, which has problems of adjustable dimension. So you can, it's the test problem, dimensions that you can adjust yourself. Now we considered 4 problems where we did our testing. We considered 3 problems are from a library, sparse problems, and the second one is a problem that my co-author wrote the code from scratch. So the first one is called Atmos mod J. Is from numerical value prediction and atmospheric modeling. Okay. This is 3D Euler or Navier-Stokes equations in atmospheric sciences. And the matrix has a size of 1 million or more. And the non-zeros are about 8 million. We have to remember, or if you're not familiar yet, I will tell you, the matrices are in these databases where we find in the libraries, database where we find matrices. They're in sparse storage where you have I, j value. So entry, position, index position, and value, only for the non-zeros. Okay? So then problem 3 is a smaller problem from 3D incompressible 3D flow. Okay, these problems are non-symmetric. Not to say that non-symmetric problems are only ones, which are important. Symmetric problems are also, but the methods we study here and we propose are for non-symmetric. They're non-symmetric matrices. And the last one, which actually is the most difficult of the problems that we solved here in our test, is the transport problem, which is a 3D finite element discretization of density coupled flow and transport. Okay? And this has more non-zeros, 23 million. So we solved these problems on a workstation. You see the speed and the memory on the top, and using C compiler. Okay. And we used also an open source library of iterative solvers, which was created in Japan. It's not very easy to understand, but it's easy to use it. My colleague was from Japan. He was familiar with it, and he was doing it. Algorithms programming, the list codes, is the library codes for Orthomin, GMRS, and value preconditioning, they were available there. We wrote the codes for the GRC MGS and GRC MGS MR. We programmed them, but we programmed them the same way, calling these functions that the list library has, similar to the list Orthomin and list GMRS codes. The stopping criterion for convergence is either the Euclidean norm becomes less than 10 to the minus 14, or a maximum number of iterations of 10,000 is reached. Okay, this is user choice. We decided to use that for our test problems. Okay. Now we want to make a comparison in terms of storage and computational complexity per iteration of the tested methods. Okay, so we have our methods, GRC MGS, J. This keeps only J vectors in store, as we said. The orthomin J, also J vectors usually stored are used. GMRS J is a restarted method, but at most it uses also in-store J vectors, actually J plus 1. And our GRCMGS MRJ uses 2J, is 2J. The reason is the direction vectors are used, the phi vectors, but also h times phi. Okay? This seems a little bit severe. Okay, thank you so much. But it's not, as you will see, because the methods need a smaller j.
What exactly means 2J is the number of vectors you store or the number of elements?
Number of vectors.
Of vectors.
Yes.
So the vectors are full size?
Full size. Yes. Size, the dimension of the problem.
Yes, thank you.
Yes. But remember, most. So we could go back to. Dimension, for example, for the Advanced problem, dimension is 1.2 million, and the number of zeros, non-zeros in the matrix is 8. Here, dimension is 1.6 million, and the matrix that is needs to store 23. So it's a lot more.
And the vectors are dense. The vector you...
Vectors are dense, yes. So dense. The matrix,
Okay.
The matrix is one, it's the most space consuming, space complexity is the matrix, and also time complexity. For matrix, time spectral multiplication is actually most. And the linear combinations are, in machine learning, we have sparse, but here no. And the linear combinations is order 2j, order 2j plus 2. Okay. And dot products is order j. They're full vectors.
Yes, at MATVEC is matrix vector multiplication. It's one per algorithm iteration.
Yes. Outer loop iteration. We don't want to do more. Of course, there is also the issue of the preconditioning. PR is a precondition matrix. So it's essentially two. One is the matrix H, and one is the PR conditioning, which is assumed to have the same sparsity as the matrix. So it's essentially two. Okay, better the results, I will, because it's too much to go to each problem, so I will only show the last problem, which is most difficult. Okay. And I will tell you that we did several tests to find with various j's. This is because this j is the number of vectors which we keep in store. So the Jacobi, which is the GRCMGS, is J3 and J5. The Orthomin with J5 and J10. The GMRS with J10 and J40, and GRCMGS MR with J3 and J5. Okay, we tried several of them, but we're interested in solving the problems up to convergence of double precision. Okay, this is too much actually. Usually people have a tolerance of 10 to the minus 9 or something like that. Okay, but we insisted to get double precision, 10 to the minus 12. Okay. So the first table, problem 4, is with incomplete review preconditioning. But 0 means that we keep the same sparsity structure as the matrix. If you put 1, 2, or 3 inside that review, it means that you increase the number of non-zeros in the preconditioning. So if you look at the first two methods, GRC and GS, with J equals 3 and 5, first we see the number of iterations, 2,764, and inside the parentheses is the time on that machine, sun and workstation. Okay? The same with the second one. Okay? So essentially, J equals 3 was faster. Okay? Then Orthomin, 10,000 means we reached 10,000 iterations, so it didn't converge to the precision we wanted, but it gave an error 10 to the minus 11, normal residual error, and 10 to the minus 12. And inside the parentheses is the time, okay, in microseconds, in seconds. And then GMRS likewise. And the last two, which is the last two rows, which is the method where we have a norm minimization method also in the preconditioning step, which is the MR method, was the best. Okay? Both in number of iterations and time. And this is without preconditioning. Actually, without preconditioning, the Jacobi method cannot succeed. With preconditioning, it succeeds. Okay? Converge that is. And here are the results in terms of plot, of graphs. So problem 4, again, we're focusing on problem 4, transport problem. And this is in terms of the number of iterations. And the full color symbol shows the method without preconditioning. So GRC, MGS 3, Orthomin 10, GMRS 40, and GRC, MGS, MR5 without preconditioning. Okay? It just succeeds before the number of iterations gets and then with the symbol, this is not full color, we have the preconditioned method, and essentially this is the best, where the MR method. Then we have the GRC MGS 3. It's similar graphs are with the time in seconds. Okay, so these are in terms of plotting the results at different norm levels and measuring the time. So analyzing the results.
Do you have any idea about the conditioning of each problem? Is it important in sparse algebra to estimate the conditioning, or
it's difficult?
It's difficult, yes.
Yes, it's very difficult. I have not succeeded. Only one or two of these shows the second problem, I believe, or yes, the conditional number is 10 to the 5.
10 to the 5.
The last one is the most difficult one. I have not succeeded to find from the authors of this paper, from this method, precondition number, and I have not tried. I have tried now because I will mention soon that we have rewritten these codes in MATLAB.
Also the rank is difficult to estimate, I think, with the models,
Right.
huh?
Yes.
Yes.
The rank? No, the rank is full rank.
They are full rank,
Yes, of course.
despite the fact that they are
No,
sparse.
they're full rank.
They are full rank,
It has
okay.
nothing to do with the sparsity. They're full rank. Are we okay with the time? Are we okay with the time?
We should.
People are leaving as
Yeah.
they cannot wait, but we're almost done.
Okay.
Sorry. Anyway, no, they're full rank problems.
It's a known or
No, it's known. They're full rank.
yes.
They're full rank. We
Yes,
assume
yes.
they're invariant.
Otherwise, we cannot solve the
Yeah, it's a
system.
linear system.
Okay,
It's
yes.
a linear system. It's not risk-squared problem. We're not dealing with risk-squared problems.
Okay.
It's linear systems, full rank, but the condition number, one of them, I know it's 10 to the 5. The last one seems to have a bad condition number because it's the most difficult one, but I don't know the condition. And I tried to find it
I guess that
in
we can.
MATLAB, but I cannot.
I
It's not
guess,
easy.
I guess that we can do an SVD if it is.
Oh yes,
But
but
then-
you need a lot of memory.
Yes, okay,
So,
okay, I see,
and my
okay.
authors
Okay,
have
I
a
see.
workstation in their
Yes.
in their office and they complain.
Yes,
They say
yes,
you
yes.
cannot do it.
Yes.
So anyway, the storage of GMRS, it needs to store essentially more vectors to ensure convergence. Why? Because GMRS J goes up to 40 vectors. You cannot achieve convergence with less than 40 vectors. Whereas GRC MGS with 5, it needs essentially 10 vectors. So in terms of work, the work is the same in terms of matrix times multiplication. If you count the iterations, of course, because one matrix vector multiplication per iteration is needed. But in terms of the other work, that is the linear combinations, GRC MGS needs 2 times the linear combinations as GMRS, for example. But still, because J is high, it's 40 in GMRS, 2 times J is only 20 in the GRC MGS. So still it's less work. And the preconditioned GRC MGS MRJ with precondition R0 solved the most difficult linear problems. And in the inner loop of this method, there is a polynomial preconditioning, obviously. There is from theory, there is this paper that says that for the symmetric case, we're dealing with the non-symmetric code, yeah, that MR is the most effective than all polynomial preconditioning. And this also explains why GRC and GS MR is much better than all the GRC methods. Okay? So there is a theoretical background for that. Conclusions. GRC provides a general framework for constructing a class of nested KSM. MGS is used to build a stable GRC MGS algorithm. Examples of GRC MGS algorithms were presented using only 1 or 2 steps of Jacobi and MR methods with modest storage and work requirements. GRC MGS were tested to solve sparse, non-symmetric, and indefinite linear problems and compared to the widely known and used GMRS and Orthomin. The test showed that our proposed methods are robust and effective as compared to these standard methods. I have to here to be fair and say that GMRS and Orthomin are not nested methods, okay? It has been observed from the beginning that the nested methods outperform the non-nested Krylov methods. Okay, so we have been fair, but still, because they're well known and widely used, we compare to those. Okay. In terms of future work, the computational kernels for the dot product have a high communication complexity for high performance computing systems. So new versions of KSM called communication avoiding methods are S-step methods, which I have originated in my PhD thesis since 30 years ago. They have become, again, now useful because Jim Demel from Berkeley and his group has spent 10 years dealing with the same methods. And so we plan to obtain communication avoiding versions of the proposed GRC algorithms to be scalable on high performance computing systems. We also plan to implement programming these proposed algorithms on HPCs, and we plan to obtain also quantum algorithms versions of nested methods. I have been thinking about this for many years in terms of algorithm design. I don't know the details of quantum computing, but I have read, and if I find a student or a collaborator ever interested in this, I have ideas, because the quantum algorithms on solving linear systems are based on Krylov methods. I have the papers, people who published these results. References for this talk are the paper which I sent my host to share it with you. And for future work, the references are my first paper on S-step iterative methods. Carson is a student of Jim Demel from Berkeley, and she has published several papers. She's now in the Czech Republic. She works at the University of Prague, I believe. And the last two papers are papers using Krylov subspace methods for quantum computing. Okay? The codes are available now in MATLAB. Okay? So we wrote the codes in the list library. Our paper also has the codes in the list library. You do not need to access the paper, the website of the paper, once you go to the Wiley website. But I already have it on GitHub, both the MATLAB, and there I have also my step methods. Okay, on GitHub. And that's it. Thank you so much for your attention. Any questions?
How slow is the MATLAB compared with the LIS?
Oh, it's fast.
It's fast.
Yes.
It's faster or it's?
I don't have right now.
You use a.
We wrote the code in MATLAB, the codes in MATLAB, and we do not have.
Compare with the same.
We have to compare on the same machine and so on. But they're pretty good.
Okay, good.
MATLAB is good and easy to understand. This, I had to learn many things to help my author who was writing the list codes, but he did not know MGS, he did not know many things.
Okay.
And I had to learn how to do it, because it's hard to explain somebody who is in Japan, do this, do that. I had to actually learn, do it. Of course, the code was with errors, but he was fixing the errors. So, okay, any other questions? I have to say that it would be a very strong point for somebody, a researcher or a student who is doing work in signal processing or other methods where there are sparse problems. If they learn how to use, not to do research. See, my goal, of course I am already almost at the end of my career, but my goal is how to take all the problems which are in the database for sparse problems and have a method to solve all of them, okay? Not to say that, this method cannot be solved. That's my goal. But somebody who has an application in signal processing or something else, they want to solve their problem. Okay, so they have to know how to simply use the available methods and get a good preconditioner, because they know the problem and they can design a good preconditioner and solve their problem efficiently to get after not so much computing time the result and plot the result and say I have a software that does this, so on. So okay, all right.
Alex, okay, so we can
Okay, just one idea, Antoni. The Krylov methods are mostly suited to sparse problems because you avoid all the inversions and you have the...
Some people in chemistry have used Krylov methods for dense problems.
For dense problems.
Yes, yes. In theoretical chemistry, I've seen that.
large problems or?
No, not very large. Or maybe they were large but maybe they were not interested that much in very high approximation. I don't know, but they were using because there is a point where depending on your computer and depending on the availability of high performance computing to you, there's a point where the dense methods cannot work, because here you have matrix vector multiply, but when you use, for example, you solve least squares problem, you order n to the fourth, in order n to the cube for LU decomposition. But here you do matrix vector multiplication. It's order n squared. So I've seen that as well. So, but I don't deal with dense problems.
For non-symmetric, I suppose. Non-symmetric problems.
I believe so.
Suppose, yes.
There were some theoretical chemists at the University of Minnesota, Truller, had mentioned that they were using iterative methods. My goal at that time, when I was young, very ambitious, was to replace the dense methods in all large problems. Is to have good iterative methods to solve all large problems, either dense or sparse. But now I know that's not easy, so I do whatever I can do. And I remember my mathematics professor, one time he was asked, how was your research going? And he said, I do Latin, mutatis mutandis. Whatever I can, you modify whatever you can modify. You achieve whatever is achievable.